Imagine a star so enormous that it shines millions of times brighter than our Sun. For millions of years, it dominates its corner of the galaxy, creating the very elements that make planets and life possible. Yet hidden deep within its blazing heart, an invisible countdown has already begun. Gravity waits patiently for the moment when even the brightest giant can no longer support itself. What happens next unleashes one of the most violent events in the universe, ending with an object so powerful that not even light can escape. This is the true story of how a giant star becomes a black hole. Long before becoming a giant star, everything begins inside a vast molecular cloud drifting through the Milky Way. These enormous clouds are composed mostly of hydrogen, with traces of helium and heavier elements left behind by earlier generations of stars. Gravity slowly gathers the gas into denser regions until one core becomes massive enough to collapse. As the cloud contracts, temperature and pressure rise dramatically. A young protostar forms, hidden inside thick clouds of dust. For hundreds of thousands of years, gravity continues compressing the growing object, preparing it for the moment nuclear fusion will ignite at its core. Eventually, the core temperature reaches nearly 15 million degrees Celsius. Hydrogen nuclei begin fusing into helium, releasing extraordinary amounts of energy through nuclear fusion. This outward energy pushes against gravity, creating a delicate balance called hydrostatic equilibrium. The newborn star has officially entered the main sequence, the longest stage of its life. Unlike our Sun, this star contains more than 20 times the Sun's mass. Its enormous gravity compresses the core more intensely, causing nuclear reactions to occur much faster. Although incredibly bright, this giant star is already burning through its nuclear fuel at an astonishing rate. Massive stars live dramatically different lives than smaller stars like our Sun. Their tremendous mass creates immense pressure inside their cores, accelerating nuclear fusion thousands of times faster. As a result, they produce extraordinary luminosity while consuming hydrogen at an incredible pace. A star that is 25 times the Sun's mass may survive only a few million years, a brief lifetime compared to the Sun's expected 10 billion years. Every second, unimaginable quantities of hydrogen transform into helium, releasing vast amounts of energy while quietly bringing the star closer to the inevitable end determined by the laws of physics. As hydrogen becomes scarce, gravity compresses the stellar core once again. Temperatures climb even higher until helium begins fusing into carbon and oxygen. Over time, the giant star creates heavier elements, including neon, magnesium, silicon, sulfur, and many others. Each new stage requires greater temperatures and lasts progressively shorter periods. These nuclear reactions transform the star into a cosmic factory, producing many of the elements that later become planets, oceans, and living organisms. Every atom of calcium in our bones and iron in our blood traces its origin to stars like this one that lived billions of years ago. Near the end of its life, the massive star develops an extraordinary internal structure, resembling the layers of an onion. At the center, the hottest core continues fusing the heaviest available elements. Surrounding it are concentric shells where silicon, oxygen, neon, carbon, helium, and hydrogen fusion continue simultaneously. Each layer burns under different temperatures and pressures, creating one of the most complex natural structures in the universe. Despite appearing stable from the outside, the star has entered its final evolutionary stage. Every passing day pushes the core toward conditions that can no longer support the crushing force of gravity. Eventually, the star begins producing iron within its central core. Unlike earlier fusion reactions, combining iron nuclei does not release energy. Instead, it consumes energy. The stellar engine that has resisted gravity for millions of years begins losing its ability to generate outward pressure. Iron steadily accumulates, creating an increasingly dense central core. While the outer layers continue shining brilliantly, disaster silently develops deep inside. Astronomers recognize this moment as the beginning of the star's irreversible collapse. Once the iron core grows beyond a critical limit, gravity will finally overpower every force resisting it. When the iron core becomes too massive, nuclear fusion can no longer provide enough pressure to support it. Gravity suddenly wins a battle that has lasted millions of years. Within less than a second, the core collapses inward at astonishing speed, reaching a significant fraction of the speed of light. Electrons are forced into protons, creating neutrons and releasing enormous numbers of neutrinos. The core's density rises beyond anything found on Earth. What had been a stable giant star moments earlier is now undergoing one of the fastest and most violent gravitational collapses in the observable universe. The collapsing core suddenly becomes incompressible under neutron pressure, causing infalling material to rebound outward. Combined with the immense flood of neutrinos escaping the core, this rebound drives a colossal explosion known as a core collapse supernova. The blast tears through the star's outer layers at thousands of kilometers per second, briefly shining brighter than an entire galaxy. Heavy elements forged during the star's lifetime are hurled across interstellar space, enriching future generations of stars and planets. Yet while the brilliant explosion captures attention, an even more extraordinary transformation continues deep within the shattered stellar core. Not every supernova leaves behind a neutron star. If the collapsing core remains sufficiently massive after the explosion, gravity continues crushing it beyond every known form of matter. The core contracts until it passes the point where the escape velocity exceeds the speed of light. An event horizon forms, marking the birth of a black hole. From the outside, no light or information can escape beyond this boundary. The brilliant giant star has disappeared forever, replaced by one of the universe's most mysterious objects. In the next chapter, we follow the newborn black hole as it begins its remarkable existence. The newly formed black hole is invisible. Unlike the giant star that once flooded space with light, the black hole emits no light of its own. Its defining boundary is called the event horizon, the point where gravity becomes so strong that the escape velocity exceeds the speed of light. Anything crossing this invisible surface can never return. From a safe distance, the black hole appears deceptively quiet. Yet hidden behind the event horizon lies one of nature's greatest mysteries. Where Einstein's theory of general relativity predicts gravity becomes unimaginably intense beyond anything experienced elsewhere. Inside the event horizon, gravity continues pulling matter inward. According to current general relativity, the collapsing core contracts toward an extremely small region where density and space-time curvature become extraordinarily large. Physicists refer to this predicted endpoint as a singularity, but they also recognize that existing theories are incomplete under such extreme conditions. A successful theory of quantum gravity may eventually describe what truly happens there. For now, the singularity represents one of the greatest unsolved problems in modern physics, reminding us that the universe still holds mysteries beyond humanity's current scientific understanding. A black hole does not simply pull on nearby objects like an ordinary massive body. Its immense gravity curves the very fabric of space-time itself. Planets, stars, gas clouds, and even light follow these curved paths. Near the event horizon, this distortion becomes so extreme that distant stars appear warped into glowing arcs through gravitational lensing. Time itself also slows relative to distant observers, an effect predicted by Einstein and confirmed through many precise experiments. Around a black hole, gravity changes not only where objects move, but also how time passes. The supernova has scattered enormous amounts of gas into surrounding space, but not all of it escapes forever. Some of the ejected material slows, reverses direction, and begins falling back toward the newborn black hole. Gravity accelerates this gas to extraordinary speeds. Instead of falling directly inward, the material usually spirals into orbit, forming a rapidly rotating disk around the event horizon. Friction within this disk heats the gas to millions of degrees, producing intense X-rays and other high-energy radiation, before the matter finally disappears beyond the black hole's invisible boundary. Although a black hole itself cannot emit light from inside the event horizon, the surrounding accretion disk can become one of the brightest objects in the universe. Gas orbiting near the black hole reaches incredible velocities, colliding with neighboring particles and converting gravitational energy into heat. Temperatures rise so high that the disk glows across the electromagnetic spectrum, from visible light to powerful X-rays. Ironically, the darkest object in existence often reveals itself through some of the brightest radiation produced anywhere in the cosmos, allowing astronomers to detect otherwise invisible black holes. As matter spirals inward, powerful magnetic fields interact with the rapidly rotating gas surrounding the black hole. Under certain conditions, these fields launch enormous jets of charged particles from the regions near the black hole's poles at speeds approaching the speed of light. These relativistic jets can extend for thousands or even millions of light years, influencing surrounding gas clouds and future star formation. Alongside these jets, energetic wands carry material away from the accretion disk. Together, these outflows demonstrate that black holes can shape their cosmic environments without anything escaping from inside the event horizon itself. Across the Milky Way, astronomers discover many stellar mass black holes because they belong to binary star systems. If a companion star orbits nearby, the black hole's gravity can gradually pull gas away from its partner. This stolen material forms a brilliant accretion disk that emits intense X-rays detectable across space. Orbiting telescopes observe these energetic signals, revealing invisible black holes through the behavior of surrounding matter. Although the black hole remains unseen, its powerful influence on nearby gas provides compelling evidence for its existence and allows scientists to estimate its mass with remarkable accuracy. Not every black hole is the same. The black hole born from a collapsing massive star typically contains several dozen times the Sun's mass and is known as a stellar mass black hole. Far larger, supermassive black holes reside in the centers of most galaxies and contain millions or even billions of solar masses. Scientists continue investigating exactly how these enormous giants formed so early in cosmic history. While they differ dramatically in size, both types obey the same physical laws described by Einstein's theory of general relativity and observational astronomy. Sometimes two massive stars form together, each eventually collapsing into its own black hole. Over millions or billions of years, these black holes gradually spiral toward one another, losing orbital energy by emitting gravitational waves. When they finally merge, they create a single, larger black hole, while releasing enormous amounts of energy as ripples in space-time itself. In 2015, the LIGO observatories made the first direct detection of gravitational waves from merging black holes, confirming another major prediction of Einstein's theory, and opening an entirely new way to study the universe. The giant star is gone, yet its story is far from over. Its supernova has scattered heavy elements across interstellar space, enriching giant molecular clouds that will one day form new stars, planets, and perhaps even life. Meanwhile, the newborn black hole continues quietly influencing its surroundings through gravity alone. One star's death has become the beginning of countless future worlds. In the next chapter, we will explore how stellar black holes interact with neighboring stars, shape their environments, and reveal themselves to astronomers studying the hidden architecture of our universe. The newborn black hole drifts through their galaxy without producing light of its own. If isolated, it becomes almost impossible to detect directly. Yet its gravity never rests. Nearby gas clouds, wandering asteroids, and even passing stars all respond to its invisible pull. Unlike the brilliant giant star that once announced its presence across space, the black hole now rules in complete darkness. Astronomers often describe these objects as silent because they reveal themselves only through their gravitational influence. Even unseen, the black hole continues shaping its corner of the Milky Way for millions of years. Many massive stars are born in binary systems, orbiting another star throughout their lives. If one collapses into a black hole, while its companion survives, an extraordinary partnership begins. As the companion ages, its outer atmosphere may expand until the black hole's gravity starts pulling gas away. This stolen material spirals inward, creating an intensely hot accretion disk. Powerful X-rays stream into space, making the system visible to orbiting observatories. By tracking the companion star's motion, astronomers calculate the unseen object's mass, confirming that only a stellar mass black hole can explain the observations. Gas, falling toward a black hole, rarely plunges straight inward. Instead, conservation of angular momentum causes it to spiral into a rapidly rotating accretion disk. Friction between neighboring layers of gas converts orbital energy into heat, raising temperatures to millions of degrees. The closer the gas moves toward the event horizon, the faster it travels and the hotter it becomes. This glowing whirlpool radiates enormous amounts of energy before the matter finally disappears beyond the event horizon. The process transforms invisible gravity into brilliant light, allowing astronomers to study otherwise hidden or else black holes across the universe. Near a black hole, gravity behaves unlike anything experienced within our solar system. Einstein's theory of general relativity predicts that clocks closer to a massive object tick more slowly than clocks farther away. Around a stellar black hole, this gravitational time dilation becomes increasingly significant near the event horizon. An observer safely distant would see processes near the horizon appear to slow dramatically. Meanwhile, someone falling inward would experience time normally from their own perspective. These remarkable effects demonstrate that gravity shapes not only motion, but also the passage of time itself. Light normally travels in straight lines through empty space, but near a black hole, the curvature of space-time bends its path. This phenomenon, known as gravitational lensing, allows massive objects to act like natural cosmic lenses. Stars positioned behind a black hole may appear distorted, brighter, or even multiplied into several images. Although stellar mass black holes produce subtle lensing effects, astronomers have observed gravitational lensing throughout the universe to measure invisible matter and confirm Einstein's predictions. Even light, the fastest traveler in nature, must follow the curved geometry created by intense gravitational fields. Astronomers estimate that the Milky Way contains millions of stellar mass black holes formed by the deaths of massive stars. Yet only a small fraction have been identified because most remain inactive, producing little or no detectable radiation. Without nearby gas to feed them or companion stars to reveal their presence, these black holes drift silently through the galaxy. New observing techniques, including gravitational microlensing and precise measurements of stellar motion, are helping scientists discover more of these hidden objects. Each discovery improves our understanding of stellar evolution and the life cycles of massive stars. The death of one giant star becomes the beginning of countless new possibilities. Heavy elements expelled during the supernova mix with interstellar gas, enriching future generations of molecular clouds. Over millions of years, gravity compresses these enriched clouds into new stars surrounded by protoplanetary disks. Rocky planets form from elements such as iron, silicon, oxygen, and carbon, materials forged inside long-dead massive stars. Every generation of stars builds upon the legacy of earlier ones, gradually increasing the chemical richness of galaxies. Stellar death is therefore an essential step in the universe's ongoing process of creation. Modern observatories study black holes using far more than visible light. Space telescopes detect X-rays emitted by hot accretion disks, while radio telescopes observe powerful jets launched near black holes. Infrared instruments peer through dust clouds hiding stellar remnants, and gravitational wave observatories detect collisions between merging black holes. Together, these complementary techniques reveal different aspects of black hole behavior. No single telescope can observe every phenomenon, but by combining information across multiple wavelengths and messengers, astronomers build a far more complete picture of these extraordinary objects than ever before. Black holes were once considered purely mathematical solutions to Einstein's equations. Over the past century, advances in astronomy have transformed them from theoretical predictions into well-supported astrophysical objects. Scientists have measured stars orbiting invisible massive companions, detected X-rays from accreting black holes, recorded gravitational waves from black hole mergers, and even captured images of the shadows cast by supermassive black holes. Each observation strengthens confidence in our understanding, while also raising new questions. Science advances through this continual cycle of prediction, observation, testing, and refinement, bringing humanity ever closer to understanding nature. A giant star's transformation into a black hole is not merely the end of a stellar life. It is a story of gravity, nuclear fusion, cosmic recycling, and the evolution of galaxies. The black hole left behind may survive for billions of years, quietly influencing its surroundings while the elements created inside its parent star become part of new stars, planets, and perhaps living worlds. What began as a collapsing cloud of hydrogen has become both an invisible, gravitational giant and a source of the materials that shape the universe. In the next chapter, we explore black holes on even larger cosmic scales. Although every black hole obeys the same physical laws, they vary enormously in mass. Stellar mass black holes form from collapsing massive stars and typically contain several to several dozen times the Sun's mass. Supermassive black holes, found at the centers of most large galaxies, contain millions or even billions of solar masses. Between these extremes, astronomers continue searching for convincing evidence of intermediate mass black holes. Understanding how these different populations form remains one of the most important challenges in modern astrophysics, linking stellar evolution to the growth of galaxies across cosmic history. Nearly every large galaxy studied carefully appears to host a supermassive black hole at its center. Our own Milky Way contains one known as Sagittarius A star, with a mass of about 4 million suns. Although currently quiet, it still dominates the motions of nearby stars. Astronomers track these stellar orbits for decades, revealing an invisible object packed into an incredibly small region. The observations provided some of the strongest evidence that supermassive black holes truly exist. Similar giants occupy countless galaxies, silently influencing their surroundings across billions of years of cosmic evolution. When a supermassive black hole actively feeds on enormous quantities of gas, it can become a quasar. These extraordinary objects produce more light than entire galaxies, despite originating from regions far smaller than their galaxies themselves. Matter spiraling towards the event horizon releases tremendous gravitational energy before crossing the boundary, powering dazzling radiation across the electromagnetic spectrum. Some quasars are visible from billions of light years away, allowing astronomers to study the young universe. Their remarkable brightness makes them valuable probes of cosmic history and the growth of early galaxies and black holes. A stellar mass black hole can grow by accreting gas or merging with other black holes, but reaching millions or billions of solar masses is an enormous challenge. Scientists continue investigating how the earliest supermassive black holes formed so quickly after the Big Bang. Proposed explanations include sustained rapid accretion, repeated mergers, and the direct collapse of massive primordial gas clouds. No single theory has yet answered every question. By studying black holes across different sizes and ages, astronomers hope to understand how the smallest stellar remnants may connect to the largest gravitational giants. If two black holes orbit one another, they slowly lose orbital energy by emitting gravitational waves. Over immense periods, their separation shrinks until they merge in a spectacular event lasting only fractions of a second. During the final moments, they release enormous amounts of energy as ripples traveling through space-time at the speed of light. These waves stretch and compress space by incredibly tiny amounts, detectable only with extraordinarily sensitive instruments. Each merger provides scientists with valuable information about black hole masses, spins, and the behavior of gravity under the universe's most extreme conditions. Traditional astronomy relies on electromagnetic radiation, such as visible light, radio waves, and X-rays. Gravitational wave astronomy adds an entirely new way to observe the universe. Instead of collecting light, detectors measure tiny distortions in space-time caused by distant cosmic events. Black hole mergers produce some of the strongest signals ever recorded. These observations allow scientists to study systems that may emit little or no light. Together, electromagnetic observations and gravitational wave measurements provide complementary perspectives, creating a richer understanding of black holes and the violent processes shaping the cosmos. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, revealing the supermassive black hole in the galaxy M87. Rather than photographing the black hole itself, the image captured glowing gas surrounding the event horizon, leaving a dark central silhouette. Later observations also produced an image of Sagittarius A star, the Milky Way's central black hole. These remarkable achievements required radio telescopes distributed across Earth, working together as one enormous virtual observatory, demonstrating humanity's ability to study even the most elusive objects in the universe. Magnetic fields play an essential role in the behavior of matter surrounding black holes. As ionized gas circles the event horizon, magnetic forces help transfer angular momentum outward, allowing matter to spiral inward. These same magnetic fields can channel enormous amounts of energy into narrow relativistic jets extending thousands of light years. Although the black hole itself generates no light, the interaction between gravity, plasma, and magnetic fields creates some of the universe's most energetic phenomena. Understanding these processes remains an active area of research in theoretical and observational astrophysics. Black holes are often imagined only as destroyers, yet their parent stars contribute profoundly to cosmic creation. Massive stars manufacture heavy elements through nuclear fusion and distribute them during supernova explosions. Black holes inherit the remnants of these stars, while the expelled material enriches future generations of stellar nurseries. Every rocky planet, every ocean, and every living organism depends upon elements forged inside ancient stars that lived and died long before our solar system existed. In this sense, stellar black holes mark both an ending and a beginning within the universe's continuous cycle of renewal. The journey from giant star to black hole is one of the universe's most extraordinary transformations. A cloud of hydrogen becomes a brilliant star. A stellar furnace creates the elements of life. Gravity triggers a catastrophic collapse, and a black hole emerges where light can never escape. Yet the story extends far beyond a single star. The explosion enriches galaxies, the black hole influences surrounding space, and the cycle of stellar birth begins again. In the next chapter, we explore how astronomers continue searching for new black holes and what these discoveries reveal about our evolving universe. Finding a black hole is one of astronomy's greatest challenges, because a black hole emits virtually no light of its own. Instead of searching for the object directly, astronomers study its effects on nearby matter. They measure the motion of companion stars, detect hot gas glowing in X-rays, observe gravitational lensing, and record gravitational waves from distant mergers. Every method reveals a different clue. Like detectives reconstructing an unseen event, scientists combine multiple observations to confirm the presence of an invisible object whose gravity alone shapes everything around it across immense cosmic distances. How can scientists weigh something completely invisible? The answer lies in gravity. If a visible star orbits an unseen companion, its speed and orbital path reveal the hidden object's mass. Using Newton's laws and Einstein's theory of gravity, astronomers calculate whether the unseen companion could be a normal star, a neutron star, or a black hole. When the invisible object's mass exceeds the maximum possible mass of a neutron star, the evidence strongly supports a black hole. Careful measurements have transformed invisible mysteries into precisely studied astronomical objects with remarkable scientific confidence. Visible light tells only part of the universe's story. Gas falling toward a stellar black hole heats to millions of degrees, producing intense X-rays invisible to human eyes. Orbiting observatories such as NASA's Chandra X-ray Observatory and ESA's XMM Newton detect these energetic signals from space. By studying changes in X-ray brightness and energy, astronomers learn how matter behaves in extreme gravity. These observations reveal the structure of accretion disks, estimate black hole properties, and test predictions of modern astrophysics. X-rays have become one of the most powerful tools for investigating stellar black holes. Sometimes a black hole reveals itself without emitting any radiation at all. If it passes between Earth and a distant star, its gravity bends the star's light through gravitational microlensing. For a short time, the background star appears brighter before gradually returning to normal. Because the lensing object may remain completely dark, this technique helps astronomers discover isolated black holes drifting through the Milky Way. Although these events are rare and difficult to observe, they provide valuable evidence that many invisible black holes roam our galaxy without nearby companion stars or glowing accretion disks. Gravitational wave observatories have transformed the study of black holes. Instead of detecting light, instruments such as LIGO, Virgo, and CAGRA measure incredibly small distortions in space-time caused by distant mergers. Each signal carries information about the masses, spins, and orbital motion of colliding black holes. Scientists compare these observations with detailed computer models to reconstruct the final moments before the merger. Every detection expands our understanding of how black holes form, evolve, and interact throughout the universe, opening a completely new era in astronomy beyond traditional telescopes alone. Some of the most important discoveries happen inside powerful supercomputers rather than observatories. Astrophysicists create detailed simulations that model the collapse of massive stars, the explosion of supernovae, and the birth of black holes. These calculations include gravity, nuclear physics, fluid motion, magnetic fields, and neutrino interactions. By comparing simulated results with real observations, researchers test competing theories and improve their understanding of stellar evolution. Although no simulation captures every detail perfectly, each generation becomes more accurate, bringing scientists closer to explaining one of nature's most dramatic transformations. Not every massive star ends with a brilliant explosion visible across the galaxy. Some evidence suggests that certain stars may collapse directly into black holes with little or no successful supernova. Astronomers call these possible events failed supernovae. Instead of becoming dramatically brighter, the star simply fades from view as its core collapses. Researchers search nearby galaxies for massive stars that mysteriously disappear without a visible explosion. If confirmed, these events would provide valuable insight into how some stellar black holes form, and why not every giant star dies in the same way. The death of massive stars has shaped the chemistry of the universe. During their lifetimes, giant stars create elements such as carbon, oxygen, silicon, and iron through nuclear fusion. Supernova explosions distribute many of these elements into interstellar space, while additional heavy elements are created through extreme nuclear processes associated with explosive environments. Future generations of stars inherit this enriched material, allowing rocky planets and complex chemistry to develop. Every breath we take and every solid surface beneath our feet exists because ancient massive stars lived, evolved, and ultimately collapsed long before Earth formed. The story of a giant star becoming a black hole is not merely about distant objects in space. It explains where many of the universe's elements originated, how galaxies evolve, and why planets capable of supporting life can exist. Black holes test the limits of gravity, while massive stars drive the chemical evolution of the cosmos. Understanding their life cycles helps scientists reconstruct billions of years of cosmic history. Each discovery connects humanity more deeply to the universe, revealing that our own existence depends on processes unfolding across unimaginable distances and timescales. Our journey has followed a giant star from its birth inside a molecular cloud to its spectacular collapse into a black hole. Along the way, we explored nuclear fusion, supernova explosions, event horizons, accretion disks, gravitational waves, and the methods astronomers use to study invisible objects. Yet many mysteries remain. Scientists continue investigating how black holes grow, how extreme gravity behaves under the most intense conditions, and what truly happens beyond the event horizon. In the next chapter, we venture even deeper into these unanswered questions at the frontier of modern astrophysics. Imagine falling toward a stellar black hole. From your own perspective, nothing special appears to happen at the exact location of the event horizon, assuming the black hole is sufficiently massive and tidal forces are not yet overwhelming. However, to a distant observer, your signals become increasingly redshifted and delayed as you approach the horizon, appearing to slow dramatically. This difference arises from Einstein's theory of general relativity. The event horizon is not a physical surface, but a boundary in space-time beyond which light and information cannot escape to the outside universe. Gravity weakens with distance, but near a stellar black hole it changes extremely rapidly over short distances. This difference in gravitational pull between your feet and your head is called a tidal force. For smaller, stellar mass black holes, these tidal forces become enormous near the event horizon, stretching objects lengthwise while compressing them sideways. Physicists sometimes refer to this hypothetical process as spaghettification. Although dramatic, it is simply the result of gravity acting more strongly on one part of an object than another, illustrating how extreme curved spacetime can become. One of Einstein's most remarkable predictions is that gravity affects time itself. The stronger the gravitational field, the more slowly time passes relative to observers farther away. This effect, known as gravitational time dilation, has been confirmed through experiments using highly accurate atomic clocks and satellite technology. Around a black hole, the effect becomes dramatically stronger. A clock close to the event horizon ticks more slowly than one far away. Although everyday life hides this phenomenon, it becomes impossible to ignore near one of the universe's most powerful gravitational objects. According to current physics, nothing that crosses the event horizon can return to the outside universe. Not matter, not light, and not information in any directly observable way. However, this statement applies only after the boundary has been crossed. Matter outside the event horizon can still orbit safely if it remains at sufficient distance. Some gas escapes entirely through powerful winds and jets launched from the accretion disk before crossing the horizon. These outflows originate outside the black hole itself, preserving the principle that nothing escapes from within the event horizon. General relativity predicts that continued gravitational collapse leads to a singularity, a region where density and space-time curvature become formally infinite. Most physicists believe this prediction signals the limits of current theories, rather than a complete description of nature. Quantum mechanics successfully explains the microscopic world, while general relativity explains gravity on cosmic scales. Inside black holes, both should matter simultaneously. Developing a theory of quantum gravity capable of describing these extreme conditions remains one of the greatest goals in modern theoretical physics, and one of science's deepest unanswered questions. In the 1970s, physicist Stephen Hawking proposed that black holes are not entirely black when quantum effects are considered. According to Hawking's calculations, black holes should emit an extremely faint form of thermal radiation, now called Hawking radiation. For stellar mass black holes, this radiation would be extraordinarily weak, making it impossible to detect with current technology. The idea combined principles from quantum mechanics, thermodynamics, and gravity, fundamentally changing how scientists think about black holes and inspiring decades of further research into their quantum nature. If Hawking radiation slowly carries energy away from a black hole over immense timescales, an important question arises. What happens to the information contained in everything that fell inside? Quantum mechanics suggests information should not simply disappear, while classical descriptions of black holes seem to imply otherwise. This apparent contradiction is known as the black hole information paradox. Researchers continue exploring possible resolutions using ideas from quantum gravity, holography, and other advanced theories. Although significant progress has been made, the complete solution remains one of theoretical physics' greatest challenges. Black holes provide natural laboratories for testing physics under conditions impossible to recreate on Earth. They allow scientists to study gravity, magnetic fields, plasma, nuclear matter, and high-energy radiation in extraordinary environments. Observations of black hole mergers test Einstein's theory with remarkable precision, while accretion disks reveal how matter behaves under immense gravitational forces. Every new observation either strengthens existing theories or exposes unexpected behavior requiring deeper investigation. Rather than merely destroying matter, black holes help scientists uncover the most fundamental laws governing the universe itself. Despite decades of research, many mysteries persist. Exactly which massive stars become black holes instead of neutron stars? How rapidly do stellar black holes grow? What determines the strength of relativistic jets? How do supermassive black holes reach enormous masses so early in cosmic history? What truly happens inside the event horizon? Every new telescope, gravitational wave detector, and computer simulation provides additional clues, yet each answer often reveals even deeper questions. Science advances not by eliminating mystery, but by steadily replacing uncertainty with better evidence and more accurate understanding. From the birth of a massive star to the formation of an invisible, gravitational giant, the story has revealed the extraordinary power of gravity and nuclear physics. Yet black holes represent more than stellar remnants. They stand at the crossroads of relativity, quantum mechanics, and cosmology. Future observatories, more sensitive gravitational wave detectors, and increasingly sophisticated simulations promise to uncover discoveries impossible today. In the next chapter, we leave theory behind and explore how black holes influence galaxies, star formation, and the long-term evolution of the universe itself, revealing their role in the grand cosmic story. For many years, astronomers viewed stellar black holes simply as the final remains of massive stars. Today, they understand these objects play a much broader role in the universe. Black holes influence nearby stars, reshape surrounding gas clouds, power energetic radiation, and participate in gravitational wave events that ripple across billions of light years. Although individually small compared to galaxies, stellar black holes contribute to the ongoing evolution of cosmic structures. Their influence demonstrates that the death of a single star can leave an imprint lasting billions of years across the universe. A supernova does far more than signal the end of a giant star. The explosion launches carbon, oxygen, silicon, iron, and many other elements into interstellar space at tremendous speeds. Over millions of years, these elements mix with giant molecular clouds drifting through the galaxy. Eventually, gravity compresses these enriched clouds into entirely new generations of stars. Around many of these stars, planets begin forming from the same recycled material. In this way, the life cycle of one massive star directly contributes to the birth of countless future planetary systems throughout the Milky Way. Earth itself owes its existence to ancient massive stars. Hydrogen and helium emerged shortly after the Big Bang, but nearly every heavier element required for rocky planets formed later inside stars. Oxygen, magnesium, silicon, calcium, and iron were forged through nuclear fusion before being scattered by stellar explosions. Without repeated generations of massive stars living and dying, planets like Earth could never have formed. Every mountain, every ocean basin, and every grain of sand contains atoms that were once part of stars that collapsed long before our solar system was born. The connection extends beyond planets to life itself. Carbon forms the backbone of organic molecules. Oxygen fills Earth's atmosphere and oceans. Nitrogen supports biological processes, while calcium strengthens bones and phosphorus helps store genetic information. These and many other elements originated through stellar nucleosynthesis and explosive stellar events over billions of years. Every living organism carries atoms created inside ancient stars. Although black holes represent the final stage of stellar evolution, their parent stars helped produce the raw materials necessary for biology. Humanity is deeply connected to the life cycles of massive stars. The Milky Way has experienced billions of years of stellar evolution. Countless massive stars have already lived, exploded, and left behind neutron stars or black holes. Astronomers estimate that millions of stellar mass black holes may now drift through our galaxy, though only a small fraction have been identified. Most remain invisible because they are isolated and not actively accreting gas. Their quiet existence reminds us that the night sky hides far more than our eyes can see. Invisible gravity silently shapes the galaxy alongside its shining stars. Dense star clusters provide ideal environments for black holes to interact. Massive stars often form close together, and after they collapse, their black hole remnants continue orbiting within the cluster. Gravitational encounters between stars and black holes can eject some objects while tightening the orbits of others. Occasionally, these interactions produce black hole binaries that later merge, generating detectable gravitational waves. By studying ancient star clusters, astronomers gain valuable insight into how stellar black holes form, move, and evolve within crowded stellar environments over billions of years. Gravity never stops shaping the universe. It gathers gas into stars, binds planets to stars, holds galaxies together, and drives the collapse that forms black holes. Even after a giant star dies, gravity continues governing every stage of its remnant's existence. It controls accretion disks, powers gravitational wave mergers, and determines the orbits of nearby stars. Unlike explosive supernovae, gravity works patiently across millions and billions of years. The story of a black hole is ultimately the story of gravity, expressing its power on the largest and most extreme scales known in nature. Modern astronomy has entered an extraordinary era of discovery. Space telescopes observe distant galaxies in infrared and X-ray light. Radio observatories map energetic jets, and gravitational wave detectors record collisions that produce no visible light. Powerful computer simulations complement these observations, allowing scientists to compare theory with reality. Together, these technologies reveal black holes with increasing precision. Every year brings new discoveries, from unexpected stellar remnants to distant black hole mergers, expanding humanity's understanding of one of the universe's most mysterious and fascinating phenomena. The next generation of observatories promises even greater breakthroughs. Future gravitational wave detectors, including planned space-based missions, will observe black hole mergers across a wider range of masses and distances. New ground-based telescopes with enormous mirrors will study stellar populations in unprecedented detail, while advanced space observatories will investigate the environments surrounding black holes across the electromagnetic spectrum. Each technological advance increases our ability to test physical theories and uncover previously hidden objects. The coming decades may answer questions that have challenged astronomers for generations. A giant star begins as a cloud of hydrogen drifting quietly through space. Over millions of years, gravity ignites nuclear fusion, forging the elements that enrich future worlds. When the fuel is exhausted, gravity triggers a spectacular collapse, producing a supernova and, for the most massive stars, a black hole. Although the star itself disappears, its influence continues through gravity, chemistry, and cosmic evolution. Its death helps create new stars, new planets, and perhaps new life. In the next chapter, we explore humanity's ongoing quest to understand these invisible giants and the mysteries they still conceal. Only a century ago, black holes existed, mainly as mathematical predictions arising from Einstein's theory of general relativity. Many scientists questioned whether such extreme objects could actually exist in nature. Decades of astronomical observations gradually changed that view. Evidence accumulated through the motion of companion stars, powerful X-ray emissions, gravitational lensing, gravitational waves, and direct imaging of black hole shadows. Today, black holes are recognized as real astrophysical objects supported by multiple independent lines of evidence. Their story demonstrates how scientific ideas become accepted through careful observation, testing, and repeated confirmation. Unlike historians studying written documents, astronomers read the history of the universe through light. Every photon arriving at Earth carries information about the object that emitted it, sometimes after traveling for millions or even billions of years. By analyzing brightness, color, spectra, and motion, scientists reconstruct the life cycles of stars and the formation of black holes. Modern telescopes function as time machines, allowing humanity to observe ancient cosmic events whose light is only now reaching Earth. Each observation adds another page to the universe's remarkable historical record. The James Webb Space Telescope has transformed astronomy by observing the universe in infrared light with extraordinary sensitivity. Although it does not observe stellar black holes directly, it studies the birthplaces of massive stars, distant galaxies, and environments where black holes influence surrounding matter. Webb's observations help scientists investigate how stars evolve, how galaxies grow, and how the earliest black holes appeared in the young universe. By looking deeper into cosmic history than ever before, it provides valuable clues that complement observations from many other observatories. Some events in the universe unfold over millions of years or occur under conditions impossible to recreate in laboratories. To study them, scientists rely on advanced computer simulations. Supercomputers solve millions of mathematical equations describing gravity, nuclear reactions, fluid motion, radiation, and magnetic fields. These simulations allow researchers to model stellar collapse, supernova explosions, and black hole formation in extraordinary detail. By comparing simulated results with telescope observations, astronomers refine their understanding of nature. Every improvement in computing power brings theoretical predictions closer to the real universe. Every major discovery raises new questions. Why do some massive stars become neutron stars while others become black holes? What determines the mass of the final remnant? How strong are magnetic fields during stellar collapse? What role do rotation and chemical composition play? Scientists continue investigating these questions using observations, laboratory experiments, and increasingly sophisticated simulations. The history of astronomy shows that each generation answers mysteries once thought impossible, while uncovering entirely new ones. Curiosity drives science forward, ensuring that the story of black holes remains far from complete. The life of a massive star reveals some of nature's most profound principles. Gravity gathers matter into stars. Nuclear fusion powers their brilliant light. Stellar evolution creates the elements necessary for planets and life. Gravity ultimately ends the star's life through catastrophic collapse, forming either a neutron star or a black hole depending on the remaining core's mass. Every stage follows the laws of physics with remarkable consistency. The transformation from star to black hole is therefore not random, but the natural consequence of the balance between gravity and nuclear energy. The story of a giant star is inseparable from the story of the universe itself. The atoms forged inside stars become part of interstellar clouds, new planetary systems, and eventually living organisms. Black holes influence nearby stars, while supernova explosions shape galaxies and enrich future generations of stellar nurseries. Every stage connects to countless others across immense distances and timescales. Rather than isolated events, stellar births and deaths form an interconnected cosmic cycle. Understanding black holes means understanding how the universe continually transforms matter and energy over billions of years. The coming decades promise discoveries that today exist only in imagination. More powerful telescopes, next-generation, gravitational wave observatories, and increasingly precise computer models will reveal details impossible to measure today. Scientists hope to discover more isolated black holes, observe stellar collapses in real time, and better understand the physics governing extreme gravity. Each technological advance extends humanity's reach deeper into the cosmos. The questions that remain unanswered today may become tomorrow's scientific breakthroughs, continuing the remarkable tradition of exploration that defines astronomy. For thousands of years, people have looked toward the stars wondering how the universe works. Today, that same curiosity drives observatories on mountaintops, spacecraft orbiting Earth, radio antennas spanning continents, and detectors capable of measuring distortions smaller than an atomic nucleus. Black holes remind us that nature still contains extraordinary mysteries waiting to be explored. Every observation expands human knowledge while inspiring future generations of scientists, engineers, and explorers. The quest to understand the universe is not merely scientific, it is one of humanity's greatest shared adventures. From a quiet cloud of hydrogen to a brilliant giant star, from a catastrophic supernova to the birth of an invisible black hole, we have followed one of the universe's most extraordinary journeys. Along the way, we discovered how gravity, nuclear fusion, and stellar evolution work together to shape galaxies and create the elements of life. Yet this story carries a deeper meaning. The death of a single star becomes part of an endless cosmic cycle that continues across billions of years. In our final chapter, we reflect on this legacy and humanity's place within the evolving universe. When a giant star dies, nothing is truly wasted. The tremendous explosion scatters newly forged elements into interstellar space, enriching giant molecular clouds that will eventually collapse into new stars and planetary systems. Even the black hole left behind continues influencing its surroundings through gravity. Across billions of years, matter is continually recycled from one generation of stars to the next. The universe is not a place of endings, but of transformation. Every stellar death becomes part of an ongoing cycle that builds increasingly complex galaxies, filled with stars, planets, and the ingredients for life. The atoms inside our bodies have traveled an extraordinary journey. Hydrogen formed shortly after the Big Bang, while carbon, oxygen, calcium, iron, and many other elements were forged inside ancient stars through nuclear fusion and explosive stellar events. These atoms drifted through space for millions or billions of years before becoming part of the cloud that formed our solar system. Today they exist within mountains, oceans, living organisms, and ourselves. The story of a giant star becoming a black hole is therefore also part of humanity's own origin story written across cosmic time. Throughout the universe, gravity works patiently without rest. It gathers diffuse gas into stars, shapes planetary systems, binds galaxies together, and ultimately determines the fate of massive stars. Unlike explosive supernovae or brilliant quasars, gravity performs its work quietly over immense timescales. The birth of a black hole represents gravity's ultimate triumph after millions of years of balance against nuclear fusion. This invisible force has shaped every major structure in the cosmos, making it one of the most powerful architects of the observable universe. Although individual stars live and die, the universe continues evolving. New molecular clouds collapse into stars while older stars exhaust their fuel. Galaxies merge, black holes collide, and fresh generations of planetary systems emerge from recycled material. This continual evolution has been unfolding for more than 13 billion years and shows no sign of stopping. The black hole born from one giant star becomes only a single chapter in a much larger cosmic story spanning unimaginable distances and timescales, revealing a universe that is constantly changing rather than remaining fixed. One of science's greatest strengths is its willingness to accept uncertainty. Astronomers have learned an enormous amount about giant stars and black holes, yet many questions remain unanswered. Exactly how some stars collapse, how magnetic fields influence explosions, and what happens inside black holes continue to challenge researchers worldwide. Rather than viewing these mysteries as failures, scientists see them as opportunities for discovery. Every unanswered question motivates better observations, improved theories, and more advanced technology, driving humanity steadily closer to understanding nature's deepest secrets. Today's discoveries will inspire tomorrow's scientists. Students watching the night sky today may become the astronomers, engineers, physicists, and astronauts who solve the mysteries still beyond our reach. Future observatories, spacecraft, and detectors will reveal details hidden from current technology, expanding humanity's understanding of black holes and stellar evolution. Scientific progress is built across generations, with each new discovery resting upon the work of those who came before. The search for knowledge continues because curiosity itself is one of humanity's greatest strengths. By studying distant stars, humanity also learns about its own origins. The chemical elements that make planets and life possible originated within ancient stellar furnaces. The gravity that formed black holes also shaped galaxies, including the Milky Way that became our cosmic home. Every observation of the universe helps answer questions about where we came from and how nature works. Astronomy is therefore more than the study of the distant objects. It is an exploration of the processes that ultimately made our own existence possible. Nearly everything we know about the universe has arrived through light or other cosmic messengers. Photons crossing billions of kilometers carry information from stars, supernovae, galaxies, and black holes. More recently, gravitational waves have added an entirely new messenger, allowing scientists to study events invisible to traditional telescopes. Together, these signals tell an extraordinary story stretching across billions of years. By carefully interpreting these cosmic messages, astronomers continue reconstructing the life cycles of stars and uncovering the hidden history of the universe itself. A single giant star may seem insignificant compared with an entire galaxy, yet its influence can extend far beyond its lifetime. It creates heavy elements, enriches interstellar space, leaves behind a black hole, and contributes to future generations of stars and planets. Through these processes, one stellar life becomes woven into the evolution of the cosmos itself. Every giant star that becomes a black hole reminds us that even individual events can have consequences lasting billions of years across vast regions of space. Our journey is nearly complete. We have witnessed the birth of a massive star, the power of nuclear fusion, the violence of a supernova, and the formation of one of the universe's most mysterious objects, a black hole. Along the way, science has revealed not only how these extraordinary events happen, but also why they matter. In the final chapter, we bring together everything we've learned and reflect on humanity's place within this remarkable cosmic story, where every ending becomes the beginning of something new. Every black hole begins with events that started millions of years earlier. Gravity gathered hydrogen into a giant molecular cloud. Nuclear fusion transformed a young star into a brilliant cosmic furnace. Heavy elements formed deep inside its core. When fusion could no longer support the star, gravity completed the final collapse. Nothing in this sequence happened by chance. Each stage followed the laws of physics, demonstrating how the universe evolves through natural processes. Understanding a black hole means understanding the entire life story of the massive star that came before it. Throughout most of a giant star's life, two powerful forces remain in balance. Gravity constantly pulls inward, attempting to compress the star. Nuclear fusion continuously pushes outward, preventing collapse. This delicate equilibrium allows the star to shine steadily for millions of years. When nuclear fuel is exhausted, that balance disappears forever. Gravity finally overcomes every remaining source of pressure, triggering one of the most dramatic transformations in nature. The birth of a black hole is ultimately the story of a balance lost after millions of years of remarkable stability. Much of the universe cannot be seen directly. Black holes emit virtually no light from within the event horizon. Dark matter remains invisible to telescopes. Gravitational waves pass silently through space. Yet invisible does not mean unknowable. Scientists reveal these hidden phenomena by measuring their effects on light, matter, and space-time. Every observation strengthens our understanding of forces operating beyond ordinary human senses. Modern astronomy has shown that the unseen universe is just as real and often even more fascinating than the brilliant stars visible in the night sky. Every major discovery about black holes began with a question. Could gravity become so strong that even light cannot escape? Do massive stars really collapse into invisible objects? Can ripples in space-time actually be detected? Generations of scientists devoted decades to testing these ideas through observation and experiment. Their work transformed speculation into evidence-based knowledge. Curiosity remains the driving force behind scientific progress, encouraging humanity to continue asking difficult questions and seeking answers through careful observation, mathematics, and the scientific method rather than assumptions alone. Although black holes seem unimaginably distant, their story is deeply connected to our own. The oxygen we breathe, the calcium in our bones, the iron in our blood, and the silicon beneath our feet all originated within ancient stars. Some of those stars ended their lives by collapsing into black holes. Their explosions enriched the gas cloud that eventually formed our solar system. In a very real scientific sense, humanity carries the chemical legacy of stars that disappeared billions of years before Earth even existed, linking us directly to the wider cosmos. The next century of astronomy promises discoveries beyond today's imagination. More powerful telescopes will study newborn stars with greater detail. Future gravitational wave observatories will detect mergers across much of the observable universe. Advanced computer simulations will model stellar collapse with increasing realism. Researchers may finally answer long-standing questions about black hole formation, quantum gravity, and the nature of space-time itself. Every technological breakthrough expands humanity's ability to explore the universe, ensuring that the story of giant stars and black holes continues far beyond our own generation. Science is not a destination, but an ongoing journey. Every solved mystery reveals new questions waiting beyond the horizon. The life of a giant star, the birth of a black hole, and the evolution of galaxies remain active fields of research where new discoveries appear regularly. Future astronomers will refine today's theories, just as today's scientists improved upon earlier ideas. This continual process of questioning, testing, and learning represents one of humanity's greatest achievements, allowing our understanding of the universe to grow steadily with each passing generation. The giant star that began this documentary no longer exists, yet its influence continues across the galaxy. Its supernova enriched interstellar space with heavy elements. Its black hole silently bends space-time through gravity. Future stars and planets will form from the material it left behind. In this way, one stellar life contributes to countless future worlds. The universe preserves nothing exactly as it was, yet it loses nothing completely. Matter changes form, energy flows onward, and the cosmic cycle continues without end. From a quiet cloud of hydrogen to a brilliant stellar giant, from a catastrophic supernova to an invisible black hole, this journey has revealed one of nature's most extraordinary transformations. It is a story written not by imagination, but by evidence gathered through generations of scientific discovery. Every telescope, spacecraft, observatory, and scientific breakthrough has helped uncover another chapter. The universe remains filled with mysteries, but each new discovery reminds us that patient observation and curiosity can illuminate even the darkest corners of existence. The story of how a giant star becomes a black hole reminds us that the universe is always changing. Stars are born, they create the elements that make planets and life possible, and the most massive eventually collapse into black holes that continue shaping the cosmos through gravity. Every discovery brings us closer to understanding our place in this vast universe, while countless mysteries still await future explorers. If you enjoyed this true documentary, please subscribe, like this video, and share it with others who love space and science. Together, let's continue exploring the incredible wonders of our universe